Hello everyone, thank you for visiting the webinar titled Debugging Multiprocessor Systems. I'm Tim Harvey, I'm a professional engineer. I write firmware all day for a living, and I will be going over these challenges of debugging multiprocessor systems and how to overcome those challenges. I know your time's valuable, so in order to thank you for spending some time with me today, I've included a little bonus at the end of this video for you, so make sure you check that out. All right, let's dive in. Anybody who writes firmware knows what it takes to debug a single processor. We usually use IDE, an integrated development environment. We burn or program our firmware into the device. We then use a debugger, which typically single steps or breakpoints or watches variables in that processor, and we can debug the program on that one processor. But what happens when the system has more than one microprocessor, or maybe an FPGA, throw a couple of other logic things in there, and before long, trying to debug some of these problems is more than just a single microprocessor's issue. And that is the core problem of debugging multiprocessor systems, is the complexity. There's many things going on, and they're all interacting at the same time. One of the biggest problems is that the existing tools that are out there on the market really expect you just to look at one processor at a time. You can get things like logic analyzers, which will show you the signals of your entire design, but it doesn't dive into the debugging of your firmware at all, unless you do a little bit of bit banging and that kind of thing. But the problem comes when we're trying to find some tools, and today we're going to show you some clever ways to get around that limitation. The limitation of having these tools is that currently we have to sync all of them together. If we have a debugger and we're trying to catch some things on the fly, maybe our Bluetooth link is breaking, we don't know why, we're going to need a logic analyzer strapped together with our firmware debugger, our IDE, and balancing all of these between the multiprocessors. We've got different languages, we've got different signal types, some are analog, some are digital. We have plenty of buses. It's just a real nightmare. So this is a real challenge. So how do we do it? So rather than step you through some boring PowerPoint presentations, I'm going to actually show you a real working system with multiprocessors in it today, and we're going to actively debug it. So this is the system I have. It's sitting here on my desk. I'll show you a video in a second. But it basically is an accelerometer-based system where acceleration is sampled, and when a hit larger than a certain percentage is achieved, a Bluetooth BLE packet is sent across to another processor. In this case, it's a Cypress BLE part, now Infineon, I believe. And this is the architecture. The accelerometer is a BMA 400 accelerometer. It's a really cool little device. It is attached to a breadboard from SparkFun. It's hosted with an ESP32 processor on it, and it's connected over an I2C bus to this accelerometer. That ESP32 board then does all the gathering of the accelerometer data, does the algorithm to figure out the magnitude, and creates a packet basically to send across the wireless Bluetooth lower energy link, the BLE link, to the other processor, the Cypress BLE 224110 module. So this is the nature of our system. We are going to go through and try to figure out how it's working and give us information on how we can debug it. Yes, well, here's the hardware that I've got on my bench. It is, blow it up here for you so you can see it. It's a real version of the block diagram on the previous sheet. I've got a SparkFun ESP32 breadboard here. I'm going to zoom in here. You can see it. Get a little focus on you. There's the ESP32. It's got a whole bunch of headers and all sorts of really good gizmos on there. Specifically, take a note of this SDA SCL line. We also have ground, obviously. We got a couple of other pins here. It says S clock and POSI on there, but we're not going to use those. We're actually going to use that for our debug output. So great board, love it. It's attached to, and let's refocus, it's attached to a BMA 400 accelerometer board. This cable is the I2C bus. It's got the SDA and SCL lines on there. I think it's got a couple other lines as well as ground and power, I believe. The other board we have here is what I'm calling the sensor hub. It is the receiving side of the BLE packets. So this system, just like I explained before, is going to gather accelerometer information. This processor is going to compute on it, and it's going to generate a packet over to the other side, the BLE side of this module, which is a microprocessor itself. And of course, I have already pinned out some of the debug lines we're going to debug with. So there's the hardware. So here we have attached the logic analyzer up to the SDA and SCL line and ground line of this board. This is the same wires that actually go across here to the accelerometer. And so we're going to switch over now to our logic analyzer to see what is going on those wires. So here's the logic analyzer we're going to use to capture this traffic on the I2C bus. I have all 7 of the logic inputs active, so we're going to capture and see, sure enough, there is traffic on this I2C bus. We'll stop the capture, we'll zoom in, and we will see what looks like I2C traffic. There's a packet, I can tell, and there's another packet a little bit longer, and there sure is enough data in there. Let's go find out what that data actually says. So we're going to go into the hardware bus decoder for channel 1 and 0, and we're going to just choose I2C. Simple as that. You press capture, and we're going to stop. We'll go into that data, zooming in, zooming in, zooming in, and sure enough, there is a packet. You can see the start bit, 29024900 stop bit. Okay, this decoder here kind of converts it into human readable form a little bit for you. This is the default I2C decoder. It's just showing that you're talking to device 14. It's a read transaction, and there's the data in that read transaction. The following one is a write. It writes address 4, and that's all it does to device 14. So there it shows you the raw data. We also can see this information over here in the right-hand side. We'll stretch that out a little bit more because it gives it a little better room. And sure enough, you can zoom around. You can go see what it's actually reading. Not really sure what this data is representing because it's coming out, for example, in this case here, we see that it's reading these 7 zeros, E4s, whatever. But I do know that it is a BMA 400 chip. So what we're going to do instead is, instead of using the packet format, which is the default for I2C, which is this here, we are going to import a different I2C packet, which is a BMA 400 definition. So if you go in this file here, and we won't dive into it now, but it's very elaborate, very detailed. You can specify registers and bit formats and all sorts of goodies. We're just going to show you the end result for this today. You can go in, and sure enough, when you zoom in, you can see that now this makes some sense. This is actually reading the X, Y, and Z access data, 10 minus 209, 54. Let's go back into this view here, and you see that sure enough, these are all the readings of the accelerometer. This particular tool is pretty cool as well, so we can zoom in and say, oh, look, I want to go to the XYZ packet right here. And if I right-click on it, I can actually graph the fields. The fields of that one then show up, and sure enough, look at that. There is accelerometer data. Let's get rid of this data here. We don't need that. That's from the previous packet. What else? Get rid of that too. So also, I don't really need this anymore. And I also don't need the analog, so let's compress those. So we're just looking at the XYZ data, and guess what? That is off of the actual I2C bus. That is extracted from the packet. Okay, and just to show you that this is coming from the actual I2C accelerometer, we're going to press a capture. It'll start gathering the data. You see it's extracting the I2C data bits here. Watch the little video down below. I'm going to do a little bit of movement, a little up and down, a little left and right, a little sideways, a little round and circle, and we're going to stop this thing. You'll see that it will packetize and decode all of that data. And as we zoom out, you see the wiggles. This is exactly what I did. You can then see, wow, how that ESP32 is actually gathering that data off the I2C bus. So this is extremely helpful, to be able to see the I2C traffic, to be able to decode it, to actually be able to graph the fields within the I2C packet. Very cool, very helpful. What's even more helpful, however, is doing this from inside the microprocessor, and we're about to show you how to do that. First thing we're going to do is we're going to hook up a couple wires on our board here. Actually, let me go in and get a little focus. We're going to pick 2 pins to send debug data from the ESP32 out the pins to the firmware debugger. We're going to write some code to tell it to send out some special commands so we can see some information from inside this microprocessor on the debugger. We're going to pick these 2 pins. You need one to be a clock, one to be data, and we are going to wire those up right now. Okay, so here we have the extra wires attached. We've got 2 of the channels going to our clock and our data. Let's focus that, a little out of focus in it. Sorry about that. 2 channels on the clock and the data coming from the microprocessor. Now let's switch over to the IDE for that processor, and let's start writing some code. And I want to show you how to do that right now. So here's the IDE for the ESP32 firmware that we wrote. It's Arduino IDE. It includes some BMA 400 accelerometer module as well as the BLE module. And it's pretty simple. It shows the setup routine, which initializes the I2C and the BLE module as well as the accelerometer. The loop is actually doing the work of this application. And as you saw in the I2C bus, it gathers the sensor data, which is over the I2C bus. It takes the magnitude of that, which is x squared plus y squared plus z squared, and it compares that against the threshold. And if it's bigger than the threshold, it actually will send a different string, ESP32 space, followed by the actual hit number, out the BLE module to the other side, to the sensor hub. So this is the application. This is what we captured on the I2C bus previously. But what we're going to do now is instead of capture that I2C bus, we're actually going to have this firmware output some data for us. And what we need to do that is we need a file called active.c. We also need an active.h. Both of these files are included on the website. We'll include a link below as well. But you include those, and you now have a couple of modules that are available to you for debugging. In the setup file, we're going to basically initialize the active interface, and we're going to do that here by adding an init call as well as sending out text. We're going to send out hello world to channel 0 text. Very simple. Okay. Now down here, since we are gathering data, I'd like to actually see some data. So let's send out, I'll copy these lines here for you. Once we read the data, let's just print it out. Kind of in the same way, we're going to send out the X, Y, and the Z data. And then let's actually also send out the magnitude. So once we compute the magnitude, let's send that out. Now what you notice is we are sending the information to different channels. So channel 1 will be all the X data, channel 2 will be all the Y, 3, so on, and 4 will be the magnitude. Okay. This, as it runs, will send out that information out to debugger. So those 4 couple lines, very simple, is all that's required. So what we're going to do is we're going to compile and build this code and run it. So there you have it, it's programmed, and now we are going to go back to the firmware debugger and analyze what we see. So first off, let's just make sure that nothing's changed. Let's go and capture again. There's our I2C data, streaming. We're going to stop it. It's going to decode it, and sure enough, there's some sensor data, okay? So let's now, instead, we now have these new wires coming out. We are going to set those up by choosing Active Debugger 2-wire. Okay, we're going to just press capture, and I'll show you what happens. So as we capture, the data that we are outputting from the microprocessor is automatically coming out and automatically be displayed in real time. You see the X data, the Y data, the Z data, and this is the magnitude, channel 4. And you can tell because look at my little window bubble of the video. As I move the sensor in real time, as I'm capturing, the data is being displayed. So you then see after the stop occurs, the I2C bus is reanalyzed and redisplayed just like we did before. And guess what? See any similarities? It's exactly the same. So we gathered the actual data off the I2C bus. We actually gathered the exact data that the microprocessor received. And then guess what? We received a curve, which is the magnitude that you cannot get off of the wires. You can only get this information in the microprocessor after it has computed the algorithm. So that's really great. We get to see that data. We get to see what's inside a microprocessor in real time live. It's wonderful. I'm going to add one more line, however, to our firmware. Let's dive back into the firmware. And I want to see when this data is actually, above the threshold. Let's see a message out that. So we're going to send out a new output. We're going to use channel 5, a brand new channel. Again, there's 64 channels on this thing. And we're going to send out a thresh. So let's just build and run this. There it's downloading. All right, and it is finished. So let's just go back to the debugger and let's, first off, let's get rid of this I2C. We don't need that anymore. Let's just capture, see what happens. So we are seeing the data. I'm going to watch my little bubble down there. I'm going to actually move it around and I'm doing some wiggles. And at some point, when I hit a threshold, guess what happens? So here you see a capture. You see it actually running the code. You see it analyzing the data. You see it outputting the threshold. And the timing of this information is exact. You can get exact timing. In this case, it was 95 milliseconds apart between hits. You can compute your algorithms. You can determine if everything is working correctly. You can see the latencies. It's very powerful. So this is a very simple example of showing you active live traffic being captured that is coming from inside your microprocessor. It's the only way, it's the only place that this information even exists. So there you have it. So again, this is all great. We're seeing a lot of good debug data, a lot of this information you probably have never seen before. You You came to this webinar, however, looking for multiprocessor debugging. And guess what? We have another one on the end of this system here. Let's fire up the camera again. We'll get the other device in the loop here. We have down here, you see the sensor hub, which is this one right there. And we are going to hook that up right now to the extra channels that are on the analyzer right here. So we're going to hook this debug port out. It's the same type of debug port. It's an active port coming out of this. It's the same as this right here. And we're going to run it into the next available channel. And look, you have 4 available possible processor connections that you can analyze all at the same time. So we're going to hook this guy up and see what happens. So there we have it. We have the sensor hub here attached to the firmware debugger with these 2 wires here. The ground is common between the USB bus, so we're not going to use the ground. The accelerometer's here, and let's see what happens. First, we're going to go into the code for this particular device and see what kind of debug output is coming out of this thing. This is the Cypress PSoC creator. It is the IDE that Infineon uses for their BLE modules. And in this particular code, I'm going to move this over here so that you can see the code. I've got a couple of modules, and in the BLE module, we have, for anyone who is familiar with the PSoC stack for the BLE, is they have a big case statement, and all of the events come through that big case statement. And one of them that is very critical for us here is when we receive a scan response from the advertising packet. It actually gives us the data that is received, and if we get any advertising packet received, we will print out what the scan response is. And you will see when I run this, it will capture all sorts of things. It captures all your speakers in your work area. It captures everyone's phone, and it will just spew tons of data. Every time one comes through, it'll spit out what it sees. Well, what we're looking for and what our device actually spits out is ESP32 space. As soon as that received, it will actually print out hey, I received the data from the other side, and here it is. So we are using what's called the active printf statement. This uses old school printf, formatting strings like %s is a string and %c is a character for those kinds of things. And we're going to get the data out of this. So let's go do it. So we are going to, let's move this up here. We are going to use the 3rd channel. The 3rd channel is the one we set up, and it is, again, an active debugger 2-wire channel. And all we have to do is press capture. We don't have to do anything. And guess what's coming out? We are getting the data. So we are going to do something now because it's starting to get complicated. We have a lot of data on the screen. So we are going to call these buses something different. In this case, this original device was the ESP32 processor. And in this case, this was the PSoC BLE part. Okay, so that when we capture this, you can see it renames. All of these signals are coming from the ESP32. All of these signals are coming from the BLE. And up here where we have it compressed, these are all the I2C transactions. So we're getting all of this data on the screen at the same time. We're getting everything from the wiggles. We're actually also even getting all of the logic pulses from all of the signals, including the debug channels. So we get a lot of data here. But what we're going to dive into is, first we'll stop this. And again, remember, it's still graphing the I2C transactions. We don't need that information anymore, so let's just hide that. But what we're going to go in here, we're going to find out how these hits work. So let's capture again. Let's see how this is doing. Let's make some data. And let's wiggle it enough that it actually, there it goes, spits out a threshold. We're going to stop that capture. We can dive into the exact area of our experiment to see where it hit the threshold. As a matter of fact, we didn't do this before, but let's do it. What was that threshold supposed to be? It was supposed to be 2,000. And look, right when it hits 2,000, boom, we hit the threshold. We spit out the data. And then guess what happens? Data comes out right here. You see it comes out 20 milliseconds later. Well, that's interesting. Why did it take 20 milliseconds? Not really sure. But look, we have 23.15 on the pulse before, and we have 20.67 on the advertising packet prior. And sure enough, when we hit the threshold, the new data came through. And if you look, it keeps the new data until yet again it hits a different threshold and a different threshold and so on. So here we are seeing 2 unique, completely independent, completely written in 2 different IDEs, two different semiconductor companies running on the exact same screen, showing exactly what's happening between the two microprocessors. Very cool. So the last feature I want to show you is current measurement. So we're going to do that by basically connecting the firmware debugger differential analog inputs right here up to the measuring posts on this particular board. This is literally nothing but the V-bus line disconnected, where they cut the trace between them, and you insert a small resistor. In this case, we chose a 3 ohm resistor, and I'll show you why. And we're going to connect that to this so that we can measure the current in real time. So bear with me while I do that. So here we have the wires going from the differential input, the analog channel 3 and channel 4 of the firmware debugger, to the measuring connection on the SparkFun board. It is, again, it is a two sides of a series resistor. In this case, it's a 3 ohm resistor that's across the V-bus line. So V-bus comes in, taps off to one wire, goes through a 3 ohm resistor, taps off this other wire, and it will measure the voltage difference across that 3 ohm resistor to compute the current. So let's do that. So the way we're going to do that is we're going to go up to the analog inputs here, and we're going to choose the channel 3-4 differential input. I like to sample a lot faster than just so I get all the data out of the waveforms, and let's press capture. Okay, there's the traffic. Now, what would you expect to be happening on our analog channel? And we're going to see. Well, if we zoom in, it's hard to see sometimes on the purple, but we are going to see what looks like, sure enough, let's blow this up. Let's get rid of some of these first. This is the current profile as the device is running of the ESP32 board. And we get to see some pulses in the current. The current is pulsing every 653 milliseconds. Not so sure why that's actually happening, but we'll find out. If you look at this, and anyone who's familiar with current characteristics, this looks like a traditional 3-channel BLE transaction at the very end. I believe they're doing a Wi-Fi transaction at the front. Not quite so sure, although I'm sure I could figure it out. But these last 3 bursts at the end are definitely BLE advertising packet channels. So what we're going to do is we are going to let's show all of these except for I2C. We're going to show the ESP, we're going to show the PSoC, we're going to show the analog channel, and let's just see what happens when this runs. Okay, we're going to wiggle. Look, see my little video down below or up above. Now you can see the activity happening. Let's hit that threshold. Boom, right there. Okay, let's go stop and let's go see what happened. So we see that the advertising channel is immediately when we hit the threshold, the BLE chip, and obviously from us transmitting the new BLE advertising string, causes a series of transactions on the current. And you can see at the end, or actually in the middle of this particular BLE pulsing, there's the scan response. So we actually see the physical power consumed while it's transmitting the packet that we got from the other side. I don't know about you, I've never seen this before. It's very helpful, very powerful. It gets both sides of the equation. It gets all the mixed signal transactions together. And with this knowledge, with this information of what's going on, you can do many things. You can optimize your battery current. You can optimize your latency in your systems. You can see why your sensor may be misbehaving when you think it's behaving. Many, many things. Very, very powerful. So yes, we have been using a new tool called the Active Pro Firmware Debugger on this example. And it is the multiprocessor firmware debugger that we've created. It's got a logic analyzer, oscilloscope. It's got hardware bus decoders with custom packet decoding. It's got current analyzer. Things you didn't see on here today is digital and analog signal generators as well. On the next page, you will see the actual pod itself. On the left is the analog inputs. We got a couple there. We got the outputs on the right. We got a couple of digital and a couple of analog outputs, creating sine waves, ramp waves, square waves, that kind of thing. The digital inputs at the end of the device down here are the core interface to your firmware debugger. Each one of the A, B, C, and D can be a separate processor. Could be an FPGA, could be a micro, could be other digital logic. It could be a I2C bus, any of those combinations. You get to capture all of them. The application that we ran today is the Active Pro software application, which shows all of the traffic, shows all of the data, decodes all of the packets, and lets you export it out into other programs like Excel or MATLAB or whatever you happen to be using. Very, very powerful. That is the tool that we have been using, and that is showing us data that we have never personally been able to see before. Hence why we're having the webinar today. So in conclusion, multiprocessor systems are a challenge. They are super fun. I absolutely love diving into systems. I personally design systems with 3, 4, sometimes even more processors. And this Active Pro has absolutely changed the dynamic of finding and solving very difficult problems. It effectively does it more than any other tool, more than any other combination of tools. Logic analyzers, oscilloscopes, a lot of bench equipment, old IDEs, which single step and breakpoint to us now seem very archaic and certainly do not show you the entire system that you need to see. We see all the data on one synchronized display. It's synchronized to the nanosecond between all of the processors. It captures and displays the data that we need to see and solve our bugs. So thank you for spending time with me today. I also thank you for any questions, comments, or suggestions you guys have. I love talking to the customers. I love talking to the community. I love doing firmware. And firmware guys, if you have some suggestions, some features that you would like to see, contact me. I just may make them happen and make this the best tool that is possible on the market. As a special thank you for watching this video and supporting Active Firmware tools, down below you'll see a special offer for one of our devices. It's the best way that I can reward you for watching this video, and it will truly be a great return on investment. It will save you time, money, and it will make you debug happy. Happy debugging.